We said that the probability that a particle is in a small region in space is equal to psi star psi times that small region in space. So let's do an example to see how we could calculate the probability that a particle is in a given region in space. Let's use a normalized wave function. We have to do that because probabilities have to add up to 1. And if I use an unnormalized wave function, then I'll get a probability that is unnormalized and doesn't add up to 1 when I add up all the probabilities. So I always have to start with a normalized wave function. So if from our last video, we know that we have a normalized wave function if we use this one that we used from the last video, and I'm just going to make n equal to 1 to make it a little bit simpler. So let's just do psi equals square root of 2 over a, that's our normalization factor, sine pi x over a, and remember that x is greater than 0 but less than a. Okay, so in this first example, let's imagine that we want to find out what is the probability that the particle is at x equals a over 4 plus or minus a over 1,000. So a over 1,000 is some small region around a over 4. So if this is my x-axis, and here is 0, and here is a, here's a over 4, a over 1,000 is some little distance around that. Okay, so this constitutes my value of dx, right? That constitutes the little region around space that I want to find where my x is, right? Okay, so what I need to do is I need to take psi star psi, so my probability at a over 4, a over 1,000 dx, right, is going to equal psi star psi. So since my wave function is not imaginary, I just square this wave function. So just square this guy here, and that will give me my probability. So 2 over a sine squared pi a over 4 a dx. So dx is a over 1,000. Okay, that's my probability. So now I just need to evaluate what that is. Okay, so I have 2 over a, and then I have sine squared of my a's divide out. So I have sine squared of pi over 4 times a over 1,000. And so these a's divide out, and I end up with 2 over 1,000 sine squared pi over 4. So sine of pi over 4 is 0.0137, and I need that squared, and then 2 divided by 1,000, and I end up with 3.8 times 10 to the minus 7 as a probability that I will find the particle at that particular point. So you'll notice that it's a really small probability, but that's because I'm looking at one point within a big domain. So now let's do this problem slightly differently. Okay, so let's imagine, first of all, let's just sort of graph out what our wave function looks like. So we have 0 and a, and if we graph sine pi x over a, we will find that we have something that looks like this, right? Can't draw it very smoothly, but you get my drift. And then if I square that, it looks like this, okay? And so let's ask the question, not the question that we just asked, which was, what's the probability that my particle is right here within a certain range? But rather, let's ask the question, what is the probability that my particle is in this whole region in space? So a big macroscopic region in space, rather than a tiny point, a whole region in space. So if I want to do that, then I need to actually integrate. I need to add up all the probabilities from this point, which is a over 2, to a. So in this case, what I'm going to want to do is the probability that my particle is from a over 2 is less than x is less than a is going to be equal to the integral from a over 2 to a of 2 over a sine squared pi x over a dx, because I'm adding up all the probabilities in that range. So now I just have to do this integral. So my probability is 2 over a, that's a constant that comes out. And then I've already looked up the integral from the integral table of sine squared bx. And in this case, my b is going to be pi over a, because that's what multiplies x. And so I end up with x over 2 minus sine of 2 pi x over a divided by 4 pi over a, and that whole thing gets evaluated from a over 2 to a. So when I do that, I get, put in a for x, so I have 2 over a, and then a in for x, so a over 2, and then minus what I get when I put a over 2 in for x. So if I put a over 2 in for x, I have a over 4. And then I need to subtract what I get when I plug in the limits to the x in my sine function. And so I end up with minus sine of 2 pi a over a divided by 4 pi over a minus sine of 2 pi a over 2 divided by a divided by 4 pi over a. Okay, so let's see what we got here. So our probability then is 2 over a, and then a over 2 minus a over 4 is equal to a over 4. So I have a over 4. And then the a cancels here, and I have sine of 2 pi. Sine of 2 pi is equal to 0. And then the a cancels here, and the 2 cancels here, but sine of pi is also 0, and so both of those terms are 0. So I end up with this, and that is just equal to, a's cancel, and I get 2 over 4, or 1/2. So that tells me that I have a 50% chance of finding the particle in this region. And that makes sense, because if you look at how we graphed this, the square of the wave function, so the probability distribution looked like this, and a over 2 is exactly half of that distribution. And so this area should be exactly half of the overall area. And if my function is normalized, the overall area is equal to 1. And so I have a 50% chance of finding it on the right half of the domain. I should also have a 50% chance of finding it on the left half of the domain.